Hello, champions! Welcome back to Crack Civil with AI, your ultimate weapon to crack TNPSCAE, SSCJE, RRBJE, GATE, and ESE with smart AI-powered explanations. If you're new here or haven't subscribed yet, do yourself a favor and hit that red subscribe button now. Press the bell and turn on all notifications. You don't want to miss a single high-yield lecture that can change your rank. Okay, let's dive right in. We're continuing our masterclass on Moment of Inertia. Today we have a really packed session. We're going to start with the absolute fundamentals. Then we'll derive the key formulas from scratch so you know where they come from. After that, we'll master the parallel axes theorem with 2 detailed numerical examples, and we'll finish up with some high-yield exam strategies that are going to give you a real edge. Let's start from the very beginning. What exactly is this thing called moment of inertia? Well, to understand the second moment of area, it helps to first understand the first. So first up, we have what's called the first moment of area. Just imagine a tiny piece of an area on our shape. We'll call it dA. If you multiply that tiny area by its perpendicular distance, let's call it y, from a reference axis, you get its first moment. If you sum all of those up for the whole shape, you get the first moment of area. This is super important for finding centroids, by the way. Now, here's where it gets really interesting. What happens if we take that area and multiply it by the distance again? Well, you get area times distance, which is area times distance squared. This is the second moment of area, and in our world of civil engineering, we call it the moment of inertia. It's basically a measure of a shape's resistance to bending. You know, think about a flat ruler. It's super easy to bend along its thin side, but try bending it along its wide side. Much harder, right? That stiffness, that's moment of inertia in action. And this right here, this is the fundamental mathematical definition you absolutely have to know. The moment of inertia, I, about an axis x, is the integral, which is just a fancy way of saying a continuous sum, of every tiny area dA, multiplied by the square of its distance y from that axis. Pretty much everything we're about to do comes from this one single definition. So how do we get those famous formulas you always see, like BD cubed over 12? Well, they don't just appear out of thin air. We don't just memorize things here, we understand them. Let's derive them from the ground up so you can tackle any problem that comes your way. Okay, to find the moment of inertia about the horizontal centroidal axis, that's just the line passing right through the geometric center, we start with our main definition. Now imagine we slice our rectangle into a super thin horizontal strip. The area of this tiny strip, dA, is just its width, b, times its tiny little height, dy. We pop that into our integral. Now pause and think, what are our limits? Since the axis is right in the middle, the strip can go from the very bottom at negative d over 2 all the way to the very top at positive d over 2. And after you solve that integral, boom, this is what you get. Champions, you need to mark this formula. Ixx equals b times d cubed all divided by 12. And listen up, that 1/12 is a standard formula value. It's a fixed universal constant derived for all rectangular sections about their horizontal centroidal axis. You can count on it in every single problem. Okay, that was for the center. But what if our axis of rotation is at the very base of the rectangle? The process is almost exactly the same. We use the same strip, dA equals b times dy. But what's the one thing that changes? It's the limits. This time, since we're measuring the distance y from the base, our strip moves from y equals 0 at the bottom all the way up to the full depth d at the top. And that one simple change in limits gives us a brand new standard formula. I base equals bd cubed over 3. Notice that coefficient is 1/3. This is another standard formula value you need to know for a rectangle's base. And it makes perfect sense that 1/3 is bigger than 1/12, right? Because on average, the area is just farther away from the base axis than it is from the center axis. So what about the vertical axis, IYY? Easy. I've got a simple trick for this. Just remember, for any axis, the dimension that runs parallel to it is to the power of 1. The dimension that's perpendicular to it gets cubed. So for our vertical axis, d is parallel and b is perpendicular. So the formula just flips to become bd cubed over 12. This is a classic MCQ trap, so don't get caught out. Deriving from scratch is fantastic for these standard axes, but what happens in an exam when they give you an axis that's somewhere totally random? For that, we need a superpower, and that superpower is called the parallel axis theorem. This amazing theorem is built on two very simple, intuitive facts. First, the moment of inertia is always at its absolute minimum value when it's calculated about the centroid. Always. Second, as you move that axis further and further away from the centroid, the moment of inertia value goes up. And it doesn't just go up, it goes up fast because it's related to the distance squared. And here it is, in all its glory. The moment of inertia about any new axis I is simply the moment of inertia about the centroid, I sub cm, plus this extra term, the total area of the shape A, multiplied by the square of the distance d between those two parallel axes. This formula is pure gold for every competitive exam out there. Okay, theory is great, but application is what gets you the marks. Let's solve a numerical problem step by step and see this theorem in action. So let's imagine we have this rectangle. We need to find its moment of inertia about an axis that's 400 millimeters below its base. Now, please remember these dimensions, the 1200 millimeter width, the 100 millimeter depth, and the 400 millimeter distance, are all assumed, arbitrary values we are using just for this example to demonstrate the calculation. In your exam, you'll use whatever values they give you in the question. First step, always, is to calculate the centroidal moment of inertia. We use our standard formula BD cubed over 12. We plug in our assumed values of B equals 1200 and D equals 1000. When we do the math, this gives us a step-by-step calculated result of 1 times 10 to the power of 8, and the units are millimeters to the power of 4. Okay, now for the trickiest part, and this is a common trap, so pay close attention. We need to find the distance D. Remember, in the theorem, D is the distance between the centroidal axis and the new axis. The centroid is at half the depth, right? 100 divided by 2 is 50 millimeters up from the base. Our new axis is 400 millimeters below the base. So the total distance is 400 plus 50, which gives us a calculated value of 450 millimeters. Don't fall for that trap. Next, we calculate that extra piece, the A times D squared term. The area A is just 1200 times 100. The distance D we just found is 450. After we calculate A times D squared, we get this value, 2.43 times 10 to the power of 10 millimeters to the fourth. Finally, we apply the theorem. We add our centroidal momi from step 1 to our AD squared term from step 3. Adding those two values gives us our final calculated result of 2.44 times 10 to the power of 10. And please don't forget the units, millimeters to the power of 4. Excellent. Let's lock that in with one more example to make sure you've got it. This time, we'll apply the theorem to a vertical axis. We're using the same rectangle, but now we're finding the moai about a vertical axis that's 1,000 millimeters to the left of the shape. And again, just to be clear, this 1,000 millimeter distance is an arbitrary value that we're using just for this solved problem's illustration. First things first, we need the centroidal moment of inertia about the vertical axis, IYY. Remember our rule from before? The formula is dB cubed over 12. This is a standard formula. And when we apply our assumed values, we get a calculated result of 1.44 times 10 to the power of 10 in millimeters to the fourth. All right, what's our distance D this time? The vertical centroidal axis is right in the middle of the width. So that's 1200 millimeters divided by 2, which is 600 millimeters from the left edge. Our new axis is 1,000 millimeters away from that same edge. So the total distance between these two parallel axes is 1,000 plus 600, which gives us a value of 1,600 millimeters. So now we just apply the theorem again. We take our centroidal moai, we calculate our new AD squared term, and we add them together. We get this final calculated result. Look how huge that number is. This really proves how rapidly the moment of inertia increases as you move that axis further and further away from the centroid. Okay, champions, let's bring it all home. We're going to recap and give you the key strategies you need to absolutely ace these questions in your exams. Here's a quick summary for you. You have to memorize these standard formulas, but what's even more important is understanding how they all relate to each other. See how you can get the base formula directly from the centroid formula using the parallel axis theorem? That's the kind of understanding that will set you apart. And please, please, please avoid these common traps. The biggest one, and I cannot stress this enough, is the first point. The parallel axis theorem is only valid if you start from ICM, the centroidal moment of inertia. You cannot use it starting from the base or any other axis. If you do that, it's a guaranteed wrong answer. This leaves us with one final thought. Look, about 70% of the questions you'll see in an exam might be direct formula applications, but it's that tougher 30%, the questions that test your core concepts, that will determine your final rank. And for those questions, a deep, conceptual understanding of where these formulas come from is your only weapon. If this detailed moment of inertia explainer helped you, do me a favor and smash that like button. It really motivates me to make more of these deep dive videos. Comment below with your biggest doubt or tell me which topic you want to see next. Share this with your friends who are also preparing. Let's crack these exams together. Remember, consistency beats talent. Keep watching, keep practicing. You've got this. See you in the next high yield lecture. Jai Hind.